A man in his backyard just broke astronomy. Paul Craggs aimed a $500 telescope at the sky and captured what NASA's billion-dollar instruments somehow missed. 3i Atlas doesn't look like a comet. It looks like something with a shell, a core, boundaries that shouldn't exist on a tumbling ice ball hurtling through space. While official observatories show us fuzzy blobs that fit the textbooks, Craggs photographed a rigid white nucleus wrapped in a smooth blue glow that resembles, and I'm choosing my words carefully here, a protective field. No tail, no chaos, just clean, geometric precision. If you stay until the end, you'll understand why scientists are quietly deleting their press releases and why this image might be evidence of something we've never seen before. If you're as captivated by this cosmic mystery as I am, go ahead and like this video and subscribe so you catch every development as this story continues to evolve. Leave a comment telling me where you're watching from, what time it is in your corner of the world, and whether you think we're being told everything about what's really passing through our solar system. Part 1. The image that broke the model. Where were you when the internet saw this? Because on a night that should have been like any other, a backyard astronomer in the United Kingdom aimed his $500 smart telescope at the sky and captured something that made NASA's million-dollar observatories look like they'd been shooting through mud. Paul Craggs, using nothing more than a Dwarf 3 telescope mounted on his patio, managed to photograph 3i Atlas in a way that has scientists quietly deleting their confident press releases and amateur astronomers flooding forums with a single question: what are we actually looking at? The image shows something that shouldn't exist according to everything we know about comets. Instead of the fuzzy, diffuse blob we expect, instead of the messy spray of dust and gas that defines these cosmic snowballs, Craggs captured a tight, rigid white core surrounded by what can only be described as a smooth, force field-like blue halo. It's clean, it's geometric, it's nothing like the chaotic organic mess that comets are supposed to be. The core sits there like a pearl in an oyster, surrounded by this perfectly symmetrical glow that looks less like sublimating ice, and more like something designed to protect whatever's inside. Traditional comets are supposed to be dirty snowballs, remember? They're chunks of ice and rock left over from the formation of solar systems, billions of years old, tumbling through space with all the elegance of a potato thrown into orbit. When they get near a star, the heat makes them sweat. Ice turns to gas, dust gets blown off, and you end up with this magnificent tail streaming behind them, sometimes millions of kilometers long, always messy, always asymmetric, always fuzzy around the edges. That's what comets do. That's what they've always done. That's what every single comet we've ever observed has looked like, from Halley's to Hale-Bopp to the hundreds of others we've catalogued over centuries. 3i Atlas was discovered on July 1st, 2025 by the Asteroid Terrestrial Impact Last Alert System telescope in Chile. Right away, astronomers knew it was special because its orbit was hyperbolic, which is the mathematical way of saying it didn't come from here. This thing came from interstellar space, from between the stars, from somewhere out there in the galaxy where we've never been and probably never will go. Only the third confirmed the interstellar visitor we've ever detected, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Each one has been stranger than the last. The official data tells us the nucleus is somewhere between 0.44 and 5.6 kilometers across. Its closest approach to the Sun, called perihelion, brought it inside the orbit of Mars, about 1.4 astronomical units from our star. Its closest pass to Earth was around 1.8 astronomical units, so no danger of impact, but close enough for us to get a really good look. And when professional observatories pointed their instruments at it, they saw what they expected to see: a comet. Fuzzy coma of gas and dust, spectral signatures of water and carbon dioxide, maybe a faint tail developing as it heated up. Nothing too unusual, nothing that would make you stay up at night wondering. But then Paul Craggs posted his image, and suddenly the official story started to feel incomplete. Because major telescopes, space-based missions, professional observatories with decades of experience and billions of dollars in funding were all showing 3i Atlas as this classical cometary object. Dust cocoon, check. Diffuse halo, check. Possible tail structure, check. Everything you'd expect from an interstellar comet making its way through our neighborhood. The images looked professional, scientifically rigorous, and thoroughly unremarkable. So what explains the disconnect? How can NASA's sophisticated instruments show us one thing while a hobbyist with a consumer-grade telescope shows us something completely different? Is this a trick of processing? Did Craggs apply filters and adjustments that exaggerated details that aren't really there? Or did his smaller, more agile setup somehow capture something that the big observatories missed, either because they weren't looking for it, or because their imaging pipelines are designed to smooth out exactly this kind of anomaly? The emotional response has been electric. Astronomers are split between excitement and skepticism. Amateur space watchers are flooding social media with their own attempts to replicate Craggs' results. Some succeeding, some failing, all arguing about what they're seeing. Conspiracy theorists are having a field day. Science communicators are trying to maintain calm while secretly wondering if maybe, just maybe, something genuinely weird is happening. The whole community is holding its breath because if Craggs is right, if that image represents something real about 3I Atlas, then we're not just looking at a comet anymore, we're looking at something that challenges the very foundation of what we think we know about these objects. Because comets don't have hard edges, comets don't maintain perfect symmetry, comets don't glow with smooth, uniform halos that look like they were rendered by a computer simulation. Comets are chaos, they're entropy, they're the universe doing what the universe does, breaking things down, spreading them out, making everything messy and complicated and beautiful in their disorder. But 3I Atlas, at least in Craggs' image, looks like order. It looks like something resisting the chaos. It looks like something that has a boundary, a shell, a structure that separates inside from outside in a way that natural objects just don't do. And that raises the central question that will haunt us through this entire investigation. Is this a trick of the camera? Aggressive. Processing, pushing pixels around until they confess to crimes they didn't commit? Or are we witnessing something fundamentally different, something unknown, something that might force us to rewrite the rules? Because in the parts ahead, we're going to explore every possibility. Technical explanations, scientific theories, even the conspiratorial ideas that most academics won't touch with a 10-foot telescope. Nothing is off the table. We're going to follow this mystery wherever it leads, and I promise you, it leads to some very strange places. The conventional model of comets, even interstellar ones, just got challenged in a way that demands we pay attention. The visuals aren't just pretty. They're demanding. They're insisting we look closer. And once you start looking closer at 3I Atlas, you realize that nothing about it makes sense. Part 2, Why NASA's official imagery looks worse. Let me show you something that'll make you question everything about how we observe space. Put the official NASA images next to Paul Craggs' backyard telescope shot, and it's not even close. The space agency's pictures show 3I Atlas as this indistinct blob, fuzzy around the edges, bleeding into the background like watercolor on wet paper. You can barely make out a nucleus. The coma blends seamlessly into space. There's no definition, no structure, no sense that you're looking at an object with boundaries. It's the kind of image you'd scroll past without thinking twice. Then you look at Craggs' image and suddenly you're staring at something that looks engineered. Sharp white core, distinct edges, that impossibly smooth blue halo that doesn't fade gradually but seems to have an actual perimeter. The difference is so stark that your first instinct is to assume one of them must be wrong. Either NASA's telescopes are failing us, or Craggs' processing is creating details that don't exist. But what if both images are technically correct, and we're just seeing two different aspects of the same impossible object? The technical constraints facing major observatories are real and significant. 3I Atlas is moving fast, incredibly fast, on its hyperbolic trajectory out of the solar system. Tracking it requires telescopes to constantly adjust their aim, fighting against Earth's rotation, fighting against the object's motion, trying to keep it centered in the frame long enough to gather photons. Ground-based telescopes have to deal with atmospheric interference, that wobbling shimmer of air that turns pinpoint stars into dancing blobs. Space telescopes don't have that problem, but they have limited observation windows and compete with hundreds of other targets demanding attention. Exposure times matter enormously. To capture a faint object moving quickly, you need to balance sensitivity against motion blur. Too short an exposure, and you don't gather enough light to see anything useful. Too long and the object smears across your detector, turning structure into streaks. Professional observatories typically use conservative settings that prioritize signal-to-noise ratio over sharpness, which means they're optimizing for detecting the object at all, rather than resolving fine detail. This is scientifically sound, but visually underwhelming. Then there's the background to consider. Space isn't empty and black. It's full of stars, galaxies, cosmic rays hitting your detector, zodiacal light from dust in the solar system, airglow from Earth's upper atmosphere if you're observing from the ground. All of that noise has to be subtracted away, and the algorithms that do this subtraction are designed to be conservative. They err on the side of removing questionable signals rather than risking false positives. The result is images that are scientifically clean but potentially missing subtle features. Enter the amateur community with their different approach. Skilled astrophotographers don't just take one picture. They take dozens, sometimes hundreds, of shorter exposures and then stack them using specialized software that aligns each frame, compensates for tracking errors, and combines the signal while averaging out the noise. This technique, called image stacking, can pull details out of data that single exposures would never reveal. Then comes deconvolution, a mathematical process that sharpens edges by essentially reversing the blurring effects of optics and atmosphere. Add contrast, stretching to make faint features visible, maybe some false color enhancement to separate different wavelengths, and suddenly you've got an image that looks nothing like what came out of the telescope originally. The question is whether these techniques are revealing reality or creating it. Deconvolution algorithms can absolutely enhance real structure, but they can also amplify noise into patterns that look meaningful but aren't actually there. Your brain is desperately good at seeing patterns. Show it random static with the slightest hint of order and it'll assemble faces, objects, structures. Processing artifacts can masquerade as cosmic phenomena very convincingly. But here's where it gets interesting. Rumour has it, and I want to be clear this is unverified, that some professional observatories did capture sharper images of 3i Atlas and chose not to publish them. The story goes that certain labs or observers got frames showing more structure than expected, more definition, maybe even hints of that hard-edged core and smooth halo, but they held back because the results seemed too anomalous, too likely to be artifacts, too potentially embarrassing if they turned out to be processing errors. Better to stick with the conservative pipeline that everyone trusts, even if it washes out interesting details. This isn't conspiracy. This is how science works when you're operating at the edge of what instruments can detect. You have two responsibilities pulling in opposite directions. First, don't publish false positives that waste everyone's time and damage your credibility. Second, don't suppress genuine discoveries just because they're surprising. Finding the balance is genuinely hard, and different teams will make different choices. The motivations are fundamentally different too. Amateur astronomers want stunning images. They want to capture something beautiful and strange that'll get shared across the internet and maybe win awards. There's nothing wrong with that, but it does create pressure to push processing as far as it'll go, to extract every last bit of detail regardless of how confident you are that it's real. Professional astronomers want scientifically defensible data. They need results that'll survive peer review, that can be independently verified, that won't make them look foolish in 6 months when better observations come in. That conservatism is valuable, but it can also be limiting. So could Paul Craggs' viral image be a legitimate better look at 3i Atlas? Absolutely possible. Smaller telescopes can sometimes outperform larger ones under specific conditions. A consumer smart telescope designed for ease of use might have automated tracking algorithms that handle fast-moving objects better than observatory systems designed decades ago for slow-moving deep-sky targets. The timing might have been perfect. The atmospheric conditions at his location that night might have been exceptional. His processing workflow might have made choices that happened to reveal real structure, rather than creating false structure. Or it could be a misleading artifact where aggressive stacking and enhancement created the appearance of a hard core and smooth halo from what's really just a slightly asymmetric coma with brightness variations. The blue color could be from wavelength separation during processing. The sharpness could be from over-aggressive deconvolution. The symmetry could be an accident of how the frames aligned during stacking. Without access to his raw data and processing pipeline, it's genuinely difficult to say. What we can say is that the difference between official and amateur images of 3i Atlas doesn't necessarily reflect objective reality. It might reflect imaging philosophy, technical choices, risk tolerance, and the eternal tension between wanting to see everything and being careful not to see things that aren't there. Both approaches have value, both can mislead, and caught between them is an object that might actually be as strange as it looks, or might be perfectly normal, and we honestly don't know which yet. That uncertainty is what makes this whole thing so magnetic. We're watching science happen in real time, with all its messiness and competing interpretations, and the answer matters more than you might think. Part 3. The missing tail problem. The real scandal. Comets have tails. That's not optional. That's not a sometimes thing. That is the defining characteristic that separates comets from asteroids, the one feature that makes them spectacular instead of just interesting. When a comet approaches the Sun and heat starts sublimating ice from its surface, gas and dust explode outward, and solar radiation pressure plus the solar wind blow that material away from the Sun in these magnificent streamers that can stretch for millions of kilometers. We've seen this thousands of times. It's one of the most reliable phenomena in solar system science. It's as close to a law as you get in astronomy. Get a comet near the Sun, you get a tail. 3I Atlas got near the Sun. Its perihelion brought it inside the orbit of Mars, well within the zone where solar heating should trigger vigorous outgassing. The official spectroscopy confirms this is happening. Data from the James Webb Space Telescope and other instruments clearly show a gas coma surrounding the nucleus, rich in carbon dioxide, some water vapor, carbon monoxide, dust particles. All the ingredients for a proper cometary display are present and accounted for. The chemistry is doing exactly what it should do. So where's the tail? Because in numerous images shared by observers, including Craggs' now famous shot, there's no visible tail. Not a faint one. Not a stubby one. Just nothing. Or in some frames, maybe the slightest suggestion of extension in one direction, so faint you're not sure if you're seeing it or imagining it. For an active comet at that distance from the Sun with confirmed outgassing, this is deeply wrong. This is the equivalent of watching water boil but never seeing steam. The physics says it has to be there, but the photographs say it isn't. Let me explain why this matters. When ice sublimes from a comet's surface, the gas doesn't just sit there forming a static atmosphere. It expands outward at speeds of hundreds of meters per second, carrying dust particles with it. The neutral gas eventually gets ionized by solar ultraviolet radiation, creating a glowing ion tail that points directly away from the Sun. The dust, being heavier, follows a curved path as it feels both the comet's tiny gravity and the pressure of sunlight pushing it back. You end up with two tails actually, the bluish ion tail straight back and the yellowish dust tail sweeping in a curve. Both should be visible, both should be obvious in any decent image. The solar radiation pressure involved is not subtle. Photons carry momentum, and when billions of them per second slam into tiny dust particles, they impart real force. For particles in the micrometer size range, typical of cometary dust, the pressure can accelerate them to speeds that overcome the comet's weak gravity completely. Within hours to days, those particles should be spread across thousands of kilometers, creating a visible coma and tail structure that grows larger the closer the comet gets to the Sun. At 3I Atlas's perihelion distance, the tail should be developing beautifully, getting brighter and longer, impossible to miss. But observers aren't seeing it, or they're seeing something so faint it barely registers. Social media and astronomy forums are filled with anecdotal reports of people trying to capture the tail and coming up empty. Some claim they see a slight elongation. Others insist there's absolutely nothing beyond that strange halo. Nobody seems to be photographing the kind of obvious, unmistakable tail structure that comet science predicts. This isn't one or two people missing it. This is a pattern of absence that demands explanation. Several possibilities present themselves, none of them entirely satisfying. Maybe the tail is being swept away extraordinarily quickly by an unusually strong solar wind during this particular period. Solar activity varies, and if 3I Atlas passed perihelion during a particularly active phase, enhanced solar wind could in theory compress and disperse the tail more rapidly than normal, but that should still leave visible coma material closer to the nucleus, and even that seems oddly faint or absent in many images. Maybe the outgassing is highly asymmetrical, with jets confined to a small area of the surface, all pointing in directions that don't produce tail material in our line of sight. Comets do sometimes have active regions rather than uniform sublimation across the whole surface. If 3I Atlas is spinning with its active jet pointed perpendicular to our viewing angle, we might miss the tail entirely, while spectroscopy still picks up the gas in the coma. Possible, but it would require very specific geometry and timing. Maybe the nucleus is unusually heavy, or covered in a thick crust that severely suppresses dust release. If the surface has been processed by billions of years in interstellar space, cosmic rays and vacuum exposure could have created a hard, non-volatile layer that insulates the ice underneath. Gas might escape through a few cracks, enough to create a coma detectable by spectroscopy, but dust production could be minimal. That would explain a faint or absent dust tail, though you'd still expect to see an ion tail from the gas itself. Or maybe something else is happening. Maybe magnetic fields generated by the comet or by interaction with the solar wind are confining the coma material, preventing it from expanding into a traditional tail. Maybe plasma effects we don't fully understand are creating a boundary layer that contains the outgassing. Maybe the dust particles are larger and heavier than typical cometary dust, so radiation pressure doesn't move them efficiently. Maybe we're seeing the birth of a completely new category of cometary behavior that our models simply didn't anticipate. What makes this so significant is that decades of cometary physics rest on the assumption that these processes are universal. We've built our understanding by observing solar system comets, and we've extrapolated those rules to predict how interstellar comets should behave. If 3I Atlas is violating those rules, it means either our physics is incomplete or this object is fundamentally different from what we've studied before. Either option forces us back to the drawing board. The missing tail problem is the real scandal here because it can't be dismissed as image processing artifacts or observer bias. Spectroscopy proves the comet is active. Conservation of mass says that material leaving the nucleus has to go somewhere. Radiation pressure and solar wind are measurable, predictable forces. Put it all together and you get a tail. Not getting a tail means something in that chain is breaking and we don't know what. Some in the community whisper that maybe the tail is there but being suppressed or hidden by that smooth halo, whatever it is. Maybe the blue glow that Craggs and others are capturing is somehow masking the dust and ion tails that should be extending behind it. If that halo is a plasma sheath or some kind of interaction region with the solar wind, it might be optically thick enough to obscure features behind it. But that's speculation on top of speculation. What's not speculation is that 3I Atlas is refusing to behave like comets should behave. It has the composition, it has the location, it has the solar heating, it has the confirmed outgassing. It should have a tail. It apparently doesn't, or has one so faint it might as well not exist. That failure is either telling us that our instruments are worse than we thought, our understanding of comets is incomplete, or 3I Atlas is something genuinely anomalous. None of those options are comforting, and all of them mean the mystery deepens with every observation we make. This object is challenging us to explain it, and so far, we're failing. Part 4. Early attempts to explain the blue halo. The smooth, symmetric blue halo surrounding. 3I Atlas's core is the feature that makes people stop scrolling and stare. It's too clean, too uniform, too unlike anything we're used to seeing around small solar system bodies. Comets have fuzzy, irregular comas shaped by the direction of sunlight, rotation of the nucleus, and asymmetric jet activity. Asteroids don't have comas at all unless they're actively breaking apart. But this thing, whatever it is, appears to have a boundary, an edge, a transition zone between inside and outside that natural objects don't typically display. So the scientific community, both professional and amateur, has been scrambling to explain it. The first hypothesis gaining traction is an ionized gas shell. The spectroscopy tells us 3I Atlas is venting carbon dioxide, carbon monoxide, and water vapor. When those molecules get hit by solar ultraviolet radiation, electrons get stripped away and you're left with ions. Ionized gas glows, often with characteristic colors depending on what's ionized and how. Carbon dioxide ions can produce bluish emissions under the right conditions. Maybe what we're seeing is a shell of ionized gas around the nucleus, fluorescing in UV light, creating that smooth blue appearance. The symmetry would come from the ions being constrained by electric fields or magnetic interactions with the solar wind, forming a more spherical structure than dust would create. The problem is that ionized gas doesn't usually form such sharply defined boundaries. Ion comas around comets tend to be diffuse, with brightness gradually falling off with distance from the nucleus. You get streamers and variations based on solar wind turbulence. The smoothness and apparent edge to the halo in Craggs's image doesn't match typical ion coma behavior. Unless there's something confining the ions, like a magnetic bubble or density discontinuity in the solar wind, it's hard to explain why the boundary would be so distinct. Enter the magnetoplasma sheath hypothesis. This idea suggests that 3I Atlas might be generating or accumulating a magnetic field that interacts with the solar wind to create a bow shock and magnetosphere, similar to what planets with magnetic fields do but scaled way down. The boundary we're seeing could be the magnetopause, where the object's magnetic influence equals the pressure from the solar wind. Inside that boundary, charged particles from outgassing get trapped and confined. Outside, the solar wind flows around the obstacle. The result would be a relatively sharp transition and a symmetric bubble shape. Sounds promising until you realize that small bodies don't generate magnetic fields. They're too small to have molten metallic cores producing dynamo action. Cometary nuclei are mostly ice and rock, neither of which is magnetic. You could argue that ionized gas flowing outward might carry frozen-in magnetic field lines from the interstellar medium that the comet traveled through, but that's exotic and requires a lot of special pleading. It's not impossible, just unlikely and unprecedented. Third possibility, image processing artifact. Maybe the blue halo is a ghost created by the way Craggs processed his stacked images. If he used aggressive contrast stretching in specific color channels, or if the stacking algorithm created a ring-shaped residual, or if deconvolution sharpening introduced a boundary where none exists in the raw data, then what we're seeing could be entirely artificial. This would be the most prosaic explanation, and would mean all the excitement is over a processing mistake. The problem is that multiple observers using different telescopes and different processing pipelines are reporting similar appearances, which suggests there's something real there, even if its nature is being exaggerated by technique. Fourth, reflective ice or frost crust. Imagine if the nucleus of 3I Atlas is covered in an unusually smooth layer of fine ice crystals or organic frost, built up over eons of interstellar travel. When sunlight hits it, instead of scattering diffusely like rough cometry, surfaces do, this smooth crust reflects light more specularly, creating a uniform glow around the nucleus. The blue colour could come from Rayleigh scattering if the particle sizes are just right, or from specific ice chemistries that preferentially reflect blue wavelengths. The sharpness would come from the fact that you're seeing reflected light from a surface rather than emission from a diffuse gas cloud. This is creative but runs into problems with the spectroscopic data. Instruments are detecting gas and dust in the coma, which means the surface is actively sublimating and ejecting material. A smooth frost crust would be disrupted by that activity, creating the exact irregular, fuzzy appearance we're not seeing. Unless the crust is regenerating constantly in real time, which seems physically implausible, this doesn't work as a complete explanation. Here's where things get really interesting. Recent polarimetric observations of 3I Atlas, before perihelion, revealed what the researchers described as an extreme negative polarization branch, a combination unprecedented among asteroids and comets. Polarization measurements tell us about the size and properties of scattering particles. Negative polarization at small phase angles typically indicates very fine dust, much smaller than the wavelength of light, or very specific surface properties. The word unprecedented is not used lightly in scientific papers. When astronomers say they've never seen this before, they mean they've compared it against thousands of other objects and nothing matches. This polarimetric oddity doesn't cleanly support any single hypothesis, but it does confirm that something about 3I Atlas's interaction with light is genuinely abnormal. Maybe the halo is fine dust so small it scatters light in unexpected ways. Maybe it's a mix of gas and nanoscale particles. Maybe there's a gradient of particle sizes creating layered optical effects. The data tells us the behavior is real and unprecedented, but not what's causing it. Let's cross-check with what else we know. The James Webb Space Telescope found the coma is carbon dioxide dominated, with dust, water and carbon monoxide also present. That composition is unusual but not impossible for an interstellar object that spent billions of years in deep space. Carbon dioxide ices would sublimate readily at 3I Atlas's perihelion distance, providing plenty of gas for a coma. Dust is confirmed to be present, though maybe in lower quantities than typical comets. But none of the leading hypotheses comfortably explains the combination of smooth blue halo, rigid core appearance, extreme polarization, confirmed gas coma, and missing tail all at the same time. An ionized gas shell doesn't explain the polarimetry or the missing dust tail. A magnetoplasma sheath requires physics we've never seen from small bodies. An image artifact doesn't explain why spectroscopy and polarimetry also show anomalies. A reflective crust doesn't explain active outgassing producing the smooth appearance. Every explanation solves part of the puzzle, but leaves major pieces unaccounted for. This is where we have to be intellectually honest. Science works by proposing hypotheses and testing them against observations. When every hypothesis falls short, one of two things is happening. Either we don't yet have the right hypothesis, or we're missing crucial data that would make everything clear. 3i Atlas might be showing us physics we understand, but in a combination we've never encountered. Or it might be showing us physics we don't understand at all. The blue halo is more than an aesthetic curiosity. It's a genuine puzzle that our current models can't comfortably solve, which means this object is hiding something we haven't yet figured out how to see. Part 5. The growing suspicion of propulsion. We need to talk about the elephant in the observatory. Some people, and I'm going to be very clear that this is speculative and unverified, but it's being discussed seriously enough that we can't ignore it, are calling 3i Atlas a craft. Not a comet, not an asteroid, a craft, as in something built, something designed, something that might have engines. The clean core and that force field-like halo don't look natural to these observers. They look engineered, they look like exactly what you'd expect from some kind of protective shell around a vessel travelling between stars at high speed. Before you dismiss this entirely, let's look at what's fueling the speculation. Start with rotational behaviour. When astronomers track small objects over time, they measure brightness changes as different parts of the surface rotate in and out of view. Irregular shapes and surface features create brightness variations that reveal the rotation period and give clues about shape. Comets and asteroids typically tumble, their rotation axes precessing over time due to torques from outgassing or radiation pressure. It's chaotic motion that reflects the fact these are passive objects responding to forces. Some observers tracking 3i Atlas have reported unusual rotational stability, what they describe as constant attitude. If true, this means the object isn't tumbling randomly, but maintaining a fixed orientation relative to its direction of travel or to the sun. That kind of stability is rare in natural objects unless they're tidally locked, which 3i Atlas can't be, because it's not orbiting anything close enough. So how do you get stable rotation? Either through very specific mass distribution that resists perturbations, or through active stabilization, meaning something adjusting the spin. Natural explanations exist, but they're not easy. If outgassing is perfectly symmetric with jets distributed evenly around the rotation axis, you could minimize torque and maintain stable spin. If the object is unusually massive and dense relative to its size, rotational inertia could resist changes. If there's no significant outgassing at all, nothing would perturb the rotation. But we know there is outgassing because spectroscopy confirms it. And perfectly symmetric outgassing is geometrically unlikely. And if it's not massive, torques should affect it. This opens a door that makes many scientists uncomfortable, but that we have to walk through honestly. If natural mechanisms for stable rotation are weak or absent, what's left? The uncomfortable answer is artificial stabilization, active control, thrusters or reaction wheels or gyroscopes or something equivalent, keeping the object pointed in a desired direction. Which would mean 3i Atlas isn't just a rock with weird optical properties. It would mean there's something inside directing its behaviour. Now let's talk composition, because this is where things get genuinely strange. The coma is unusually rich in carbon dioxide, with one of the highest carbon dioxide to water ratios ever measured for a comet. Most solar system comets are water-dominated. They're ice from the early solar system that formed beyond the frost line, rich in water ice with lesser amounts of other volatiles. Carbon dioxide is present, but usually as a minor component. 3i Atlas flips that ratio. What does that mean? One interpretation is that this object formed in a different environment, maybe around a different star with a different protoplanetary disk composition. Maybe it comes from a system where carbon dioxide ices were more abundant than water ices, which could happen if the formation region was colder or had different initial chemistry. That would make it naturally exotic, but still a natural object. But there's another interpretation that the more speculative researchers are pushing. What if the high carbon dioxide ratio reflects processing? What if the surface has been deliberately modified or naturally altered in ways that concentrate carbon dioxide at the expense of water? Cosmic ray bombardment over billions of years can convert carbon monoxide into carbon dioxide and build up complex organic molecules. If 3I Atlas spent eons cruising through interstellar space, radiation could have transformed its surface chemistry completely. The resulting crust might be rich in carbon dioxide and organics, with water locked deeper inside, inaccessible until the crust erodes. That's natural, but creates an unusual composition that doesn't match anything else we've seen. Or, and this is where we venture into serious speculation, what if the composition is engineered for a purpose? Carbon dioxide sublimes at higher temperatures than water ice, providing thrust at greater distances from stars. Carbon dioxide gas is less visible than water vapor and doesn't produce as much dust. If you were designing a probe to travel between stars using solar heating for propulsion and wanting to remain relatively stealthy, minimizing dust and maximizing gas thrust, a carbon dioxide-rich exterior would be a reasonable choice. That requires assuming intelligent design, which is an extraordinary claim requiring extraordinary evidence, but the compositional data doesn't rule it out. Enter Avi Loeb. The Harvard astrophysicist has built a reputation for being willing to seriously consider possibilities that most of his colleagues dismiss. He's proposed that Oumuamua, the first interstellar visitor, might have been artificial. He's advocated for searching for technosignatures, and according to news reports, he's publicly stated that 3I Atlas represents a wild comet claim that could be relevant to discussions about alien visitation. He even accepted a public wager tied to alien predictions, specifically citing 3I Atlas as a case that might prove interesting. Loeb's involvement lends a certain credibility to the speculation, not because he's always right, but because he's willing to ask questions that others avoid. His argument goes something like this. If you saw an object with no tail, unusual composition, possible stable rotation, a smooth protective shell, and behavior that doesn't quite match natural expectations, when do you start considering artificial origins? His answer is sooner than most scientists would. Most researchers want overwhelming proof before entertaining such ideas. Loeb argues we should investigate the possibility seriously, rather than dismissing it by default. The arguments in favour of the craft hypothesis stack up intriguingly. Unusual composition suggesting possible engineering or extreme processing, lack of visible tail despite confirmed outgassing, suggesting non-standard dust production or some kind of confinement, rigid core and smooth halo suggesting structural integrity and protective shell, possible stable attitude suggesting active control, historical context of previous mysterious interstellar visitors like Oumuamua that defied easy explanation, and the simple statistical argument that if technological civilizations exist and build interstellar probes, we should eventually see one, and it would probably look strange and unfamiliar. The counter-arguments are equally strong. No peer-reviewed evidence exists for non-gravitational acceleration beyond what standard cometary outgassing would produce. Major space agencies still officially treat 3I Atlas as a comet. There's no confirmed direct evidence of thrusters, onboard systems, artificial geometry, or any technosignature. The unusual features, while genuinely unusual, don't definitively require artificial explanation when natural exotic explanations remain possible. And extraordinary claims do require extraordinary proof, which we simply don't have yet. But here's the thing that keeps this possibility alive. We've never seen anything quite like 3I Atlas. The combination of anomalies doesn't match our templates. Maybe that's because we don't have enough templates yet, and we're just seeing natural diversity we didn't know existed. Or maybe it's because one of our templates should include the possibility of artificial objects from other civilizations, and we've been systematically ignoring that category even when evidence presents itself. The idea that 3I Atlas could be a craft is definitely not mainstream. It's probably not even minority opinion among working astronomers. But the combination of anomalies has reopened that door just enough that serious people are peeking through, wondering what they'd see if they looked honestly without reflexive dismissal. In the next act, we're going to dig into the actual data, the orbital modelling, the independent analyses from researchers who aren't afraid to ask uncomfortable questions. We're going to see what holds up under the harshest scrutiny, and what dissolves into wishful thinking. Whatever. 3I Atlas truly is. It's forcing us to ask deeper questions about what we expect to find travelling between the stars, and whether we'd recognise something truly alien if it showed up in our cosmic neighbourhood. Sometimes the most important scientific discoveries start with someone asking a question everyone else thought was already answered. Part 6. Deconstructing the image. What survives forensic analysis? Here's the uncomfortable truth about modern astrophotography. You can make almost anything look like almost anything else if you're willing to push the processing far enough. Colours can be invented, edges can be sharpened until they're sharper than reality. Noise can be smoothed until it becomes indistinguishable from signal. Artifacts can be enhanced until they look like features. This is why, when something as dramatic as Paul Craggs' image of Three-Eye Atlas starts circulating, the first question serious researchers ask is, what are we actually looking at? What's real and what's artifact? What survives when you strip away the processing and look at the raw data? Raw data in astronomy means FITS files, Flexible Image Transport System format, the standard for scientific imaging. These are unprocessed frames straight from the detector, with minimal correction beyond removing detector bias and dark current. No colour manipulation because most astronomical CCDs are monochrome, and colour comes from filters. No contrast stretching, no sharpening, just photon counts for each pixel, along with metadata about exposure time, filter, telescope pointing, date and time. When you want to know what's really there, you start with FITS files and work forward carefully, documenting every step. The publicly available data sets for Three-Eye Atlas include observations from the James Webb Space Telescope, various ground-based professional observatories, and heliophysics missions like STEREO with its wide-field heliospheric imager. These instruments captured Three-Eye Atlas at different wavelengths, different times in its approach and departure, different angular resolutions. What do those official datasets show? Gas coma, definitely present, with spectral emission lines from carbon dioxide, water, carbon monoxide, dust continuum. Asymmetric coma shape, elongated in certain directions suggesting active regions or jet activity. Diffuse emissions that fade gradually with distance from the nucleus, everything you'd expect from an active comet. Critically, those official datasets do not show the neat core plus halo structure that dominates the amateur images. They show fuzzy, extended irregular coma. The difference is stark and demands explanation. Either the processing applied to create the viral images is adding structure that doesn't exist, or the official pipeline is removing structure that does exist, or we're seeing two different aspects of the object at different times or wavelengths. All three possibilities have precedent. Independent analysts in the pro-amateur community, the skilled astrophotographers who straddle the line between hobbyist and professional, have started doing their own forensic work. Some have obtained or created minimally processed versions of the same data, stripping away compression artifacts, over-sharpening, aggressive colorization. Their findings, shared mostly through forums and Discord servers rather than formal publications, suggest that after removing aggressive processing, a faint core and faint halo structure sometimes survive. Not as dramatic as the viral images show, far more subtle but potentially present. These claims are anecdotal, not peer-reviewed, and could themselves be influenced by confirmation bias or processing artifacts in the deprocessing workflow. But they suggest the structure might not be entirely invented. Then we have the polarimetric study, which is peer-reviewed and published and deeply strange. The VLT, Very Large Telescope, along with the Nordic Optical Telescope and Alfoski instrument, captured polarimetric observations of Three-Eye Atlas pre-perihelion. Polarimetry measures how light's electric field is oriented after scattering from an object, which tells you about particle sizes, surface roughness, composition. Different materials and structures produce characteristic polarization signatures. What they found was described as a deep and narrow negative polarization branch, a combination unprecedented among asteroids and comets. Let me explain what that means in practical terms. When light scatters from small particles, it becomes polarized to varying degrees depending on the scattering angle. At small angles, close to straight-on viewing, many materials show negative polarization where the electric field is oriented perpendicular to the scattering plane. As the angle increases, polarization typically becomes positive. The shape and depth of this curve tells you about particle properties. Three-Eye Atlas showed unusually deep negative polarization, deeper than almost any other small body, and the feature was narrow, meaning it changed rapidly with angle. This combination suggests scattering from extraordinarily fine-grained material, particles much smaller than typical cometary dust, or from surfaces with very specific optical properties that we rarely encounter. Fine particles could be nanoscale dust in the coma, or they could be microstructures on the nucleus surface, or they could be ice crystals with particular geometries. The unprecedented nature means we don't have a template that matches it cleanly. Does this polarimetric result support the clean core plus halo claim? Indirectly, maybe. If the halo is composed of extremely fine dust or droplets, smaller than typical cometary particles, that could produce both the unusual polarization and the smooth visual appearance. Fine particles scatter light more uniformly, without the texture and irregularity that larger grains create. You could get a smoother, more symmetric coma from fine dust than from the chunky, irregular particles most comets eject. But this doesn't prove a rigid core, doesn't prove artificial structure, doesn't prove anything beyond weird scattering properties that we need to explain. There's also the possibility of observational filtering bias. Maybe the dramatic images get shared and discussed precisely because they're dramatic, while the boring, conventional-looking images get ignored. Cognitive biases would reinforce this, where people remember and emphasize the anomalous while forgetting the ordinary. If 90% of observers see a normal fuzzy comet, and 10% claim to see structure, it might just be that the 10% are wrong or processing differently. But it could also mean the 10% caught a particular viewing geometry, or atmospheric condition, or timing that revealed something real that the 90% missed. The forensic conclusion is frustratingly ambiguous. Under minimally processed data scrutiny, 3i Atlas doesn't clearly show the rigid core and force field halo that the viral images display. The official data from major instruments show a more conventional, if compositionally unusual, cometary coma. But the polarimetric data confirms that scattering behavior is genuinely unprecedented, which means something about this object is legitimately strange. Whether that strangeness is sufficient to explain the dramatic visual appearance, or whether processing artifacts are exaggerating subtle features into dramatic ones remains genuinely uncertain. What we can say confidently is that 3i Atlas doesn't fit neatly into the classic comet category. Its composition, polarization, and possibly subtle structural features place it outside the distributions we're used to. It's not obviously artificial based on minimally processed data, but it's not comfortably natural either. It occupies this uncomfortable middle ground where both natural exotic explanations and more radical possibilities remain on the table. The forensic analysis neither confirms the sensational claims nor provides a neat conventional explanation. Instead, it shows us an object that behaves unlike anything we've studied before, even when we're being maximally skeptical and conservative. That by itself is significant. That by itself means 3i Atlas has earned its place as one of the strangest objects ever detected visiting our solar system, and we still don't know what it really is. Part 7. The silent race to model its trajectory. Numbers don't lie, but they can be maddeningly ambiguous. While everyone's been focused on the images, a quieter, more technical race has been happening in the background. Orbital dynamicists, the researchers who calculate trajectories and predict where objects will be, have been meticulously tracking 3i Atlas as it sweeps through the inner solar system. Because here's the thing about orbits. They're extraordinarily sensitive to forces. Even tiny accelerations, fractions of a millimeter per second squared, accumulate over time and show up as deviations from purely gravitational predictions. If 3i Atlas is experiencing forces beyond gravity, the orbit will tell us. And if those forces can't be explained by natural comet physics, we're in very interesting territory. The known orbital facts establish the baseline. 3i Atlas is on a hyperbolic trajectory with an eccentricity greater than 1, which mathematically means it's not bound to the Sun and will eventually leave the solar system forever. At discovery, it was moving at roughly 221,000 km per hour, about 60 km per second relative to the Sun. Its perihelion, closest approach to the Sun, occurred around 1.4 astronomical units, inside the orbit of Mars but well outside Earth's orbit. Closest approach to Earth was approximately 1.8 AU, close enough for excellent observations but far enough to pose zero danger of impact. Orbital modelers need high-precision astrometry to build accurate trajectories. That means time-stamped position measurements from multiple observatories, ideally spanning weeks or months, covering different parts of the orbit. Each position measurement has uncertainty, error bars reflecting telescope resolution, atmospheric seeing, timing precision. By fitting all the measurements together, you build a solution for the orbital elements: semi-major axis, eccentricity, inclination, longitude of ascending node, argument of perihelion. For an object moving in pure Keplerian motion under gravity alone, these elements stay constant. Measure them once, predict the orbit forever. But comets don't move in pure Keplerian motion. Outgassing produces jets of gas and dust that push back on the nucleus, creating non-gravitational forces that alter the orbit slightly. The effect is real, measurable, and actually helps us understand comet physics. By measuring how much the orbit deviates from pure gravity, you can estimate the strength and direction of outgassing jets, which tells you about nucleus rotation, active regions, mass loss rates. Standard comet modelling includes these non-gravitational parameters as part of the solution. Behind the scenes, in private communications, pro-amateur astronomy communities on Discord and Slack, university research groups, there's been intense activity around 3i Atlas's orbital solution. People are sharing data, comparing results, checking residuals, the differences between predicted and observed positions. Some are speculating openly about whether the published orbital solutions include adequate non-gravitational terms, or whether there are unexplained accelerations hiding in the residuals. This is speculative regarding the human behaviour, but entirely plausible given the interest and the accessibility of astrometric data. If 3i Atlas showed slight acceleration or deceleration beyond what gravitational interactions with the Sun and planets predict, what would that imply? The conventional explanation is outgassing jets, same as every other active comet. Gas molecules leaving the surface carry momentum. If jets point backward relative to the direction of travel, they speed the comet up. If they point forward, they slow it down. Asymmetric outgassing creates torques that change rotation. This is well understood physics, observed in dozens of comets, completely natural. Radiation pressure from sunlight also matters, though usually at very low levels. Photons carry momentum, and when they reflect off the nucleus or get absorbed and re-emitted, they push. The force is tiny but measurable for small objects. Solar wind, charged particles streaming from the Sun contributes additional pressure. For a small low-mass nucleus, these forces combine to create measurable but predictable deviations from Keplerian motion. But what if the deviations don't match the expected pattern? What if the acceleration is stronger than outgassing should produce given the observed coma brightness? What if the direction is wrong, not aligned with the subsolar point or rotational axis? What if there's unaccounted momentum exchange that standard models can't explain? Then you start asking uncomfortable questions. The spectroscopy confirms a coma rich in carbon dioxide, carbon monoxide, water and dust. That should produce outgassing with enough thrust to perturb the orbit measurably. Carbon dioxide sublimation at 3i Atlas's distance generates significant vapor pressure. If the nucleus is a few kilometers across with typical cometary density, mass estimates suggest outgassing forces should be comparable to what other comets experience. So any non-gravitational acceleration should be explainable within that framework. But remember, the polarimetric data suggesting unusually fine dust and unprecedented scattering properties. What if the dust particles are so fine that they're ejected gently rather than explosively? What if outgassing is vigorous but produces minimal momentum change because the gas escapes symmetrically or the particles are too small to carry much momentum? What if the coma is dusty and gassy but the forces somehow balance out, resulting in little net acceleration? These are ad hoc explanations, but they're not impossible. Alternative scenarios exist that are more exotic. Scenario 1. Outgassing is symmetric, uniform across the surface, producing no net torque. The nucleus maintains stable rotation because no unbalanced forces perturb it. This requires implausibly perfect symmetry but isn't ruled out. Scenario 2. The object is internally structured, maybe with a dense core or unusual mass distribution that resists torque. High rotational inertia would make it harder for outgassing jets to change spin. Plausible if the nucleus is unusually dense or compositionally layered. Scenario 3. The object is physically massive, much denser than typical comets, so mass loss and momentum exchange have negligible effect on rotation and trajectory. If 3i Atlas is mostly rock or metal with only a thin ice veneer, it could be effectively immune to small forces. This would make it more like an asteroid than a comet, except for the confirmed outgassing. Scenario 4. Radiation pressure is relatively weak because the particle sizes or albedo don't couple efficiently to sunlight. Large, dark particles feel less radiation pressure than small, bright ones. Or Scenario 5. Non-natural forces are acting. Thrusters, adjustments, active control. This requires assuming artificial origin, which is the most extraordinary claim and requires the strongest evidence. But if natural mechanisms can't explain stable rotation and trajectory anomalies, this hypothesis moves from ridiculous to merely unlikely. The critical point is that at present, there's no public, peer-reviewed, widely accepted claim of anomalous trajectory changes attributable to artificial thrust. The orbital solutions published so far describe 3I Atlas as moving under gravity plus standard cometary non-gravitational forces. The residuals, the small differences between prediction and observation, appear to be within expected bounds given measurement uncertainties. So from a mainstream perspective, the orbit looks normal for an active comet. Nothing to see here. But the absence of published anomalies doesn't mean no one is looking, or that anomalies don't exist. It means either they haven't been found, or they're too subtle to claim confidently, or they exist but are being withheld pending further verification. Orbital analysis is meticulous, slow work. Premature claims damage reputations. If someone suspects an unexplained acceleration but isn't certain it's real, rather than systematic error in their measurements, they'll stay quiet until they're sure. The data landscape remains open enough that careful modelers are paying attention, running their own analyses, checking whether the official solutions fully capture what's happening. Upcoming observations matter enormously as 3I Atlas moves. 3I. Outbound, post-perihelion, into different viewing geometries and distances, continued tracking will refine the orbital solution. If non-gravitational effects are present, they'll accumulate and become more obvious with time. If outgassing continues far from the Sun, that's unusual and interesting. If it shuts down abruptly, that tells us about surface properties. Different vantage points, different observatories, longer time baselines all contribute to building confidence in what forces are really acting on this object. The orbit of 3I Atlas, carefully tracked with extreme precision, might hold the biggest clues we'll get. Images can be processed and misinterpreted. Composition is interesting but ambiguous. But trajectory integrates everything the object is experiencing, every push and pull, into a single mathematical story. If natural forces completely explain the orbit, the exotic hypotheses become much weaker. If natural forces fall short, if there are persistent residuals or accelerations pointing in strange directions, then we're forced to consider radical alternatives. The numbers will tell us, eventually, if we're patient and careful and honest about what we're seeing. Part 8. Patterns that match nothing natural. Let's put 3I Atlas in context because cosmic visitors didn't start with this one, and the pattern of strangeness is becoming hard to ignore. October 2017, a telescope in Hawaii detected an object moving fast through the inner solar system on a hyperbolic trajectory. It was named 1I/Oumuamua, meaning scout or messenger in Hawaiian, and it became the first confirmed interstellar object ever detected passing through our solar system. Nothing about it made sense. The light curve showed brightness variations suggesting an elongated shape, maybe 10 times longer than wide, either a cigar or a pancake. No coma, no tail, no sign of outgassing, so not a comet. But its trajectory showed slight acceleration that couldn't be explained by gravity alone. Researchers proposed explanations ranging from outgassing so faint we couldn't detect it, to radiation pressure acting on an unusually flat shape, to more exotic ideas involving hydrogen icebergs or even artificial solar sails. The debate never resolved satisfactorily. Oumuamua left the solar system before we could study it properly, leaving behind more questions than answers, and a permanent reminder that interstellar space might send us visitors we're not prepared to understand. Then came August 2019. Crimean amateur astronomer Gennady Borisov detected another interstellar visitor, 2I/Borisov. This one looked exactly like what astronomers expected. A classic comet with a beautiful coma, gas and dust tails, composition similar to solar system comets. It behaved normally, followed predictions, gave us spectra and images that matched our templates. Borisov was the control case. the proof that interstellar comets could be ordinary. For a while, people relaxed, thinking maybe Oumuamua was just a statistical oddity, and interstellar visitors would mostly be boring. 3i Atlas shatters that comforting narrative. It's not Oumuamua, no coma-free asteroid-like object with unexplained acceleration. It's not Borisov, no conventional dusty comet following the playbook. Instead, it shows aspects of both, and aspects of neither. Coma present? Check, so it's outgassing like a comet. Dust detected? Check, but tail absent or minimal? Strange. Core apparently rigid and defined? Strange. Halo smooth and symmetric? Unprecedented. Composition carbon dioxide dominated? Unusual. Polarization deeply negative and narrow? Unprecedented. It's a hybrid that doesn't fit our categories. Compare it to other solar system object classes to see how poorly it matches. Centaurs are icy bodies orbiting between Jupiter and Neptune, transitional between asteroid and comet behavior. They sometimes show cometary activity when solar heating warms them. But centaurs are captured into our solar system, not interstellar, and their composition reflects formation in our own protoplanetary disk. Trans-Neptunian objects, the icy worlds beyond Neptune's orbit, are pristine relics from solar system formation. Some are large like Pluto, some tiny, most covered in methane or nitrogen ices that 3i Atlas doesn't show. Their reflectance spectra are distinct, their dynamics are different. High albedo asteroids, the bright ones, are usually rocky or metallic bodies that reflect sunlight efficiently. They don't outgas because they lack volatiles. Their polarization curves are different, showing positive polarization at small angles, unlike 3i Atlas's negative branch. Quasi-satellites, objects in strange resonant orbits with planets, are dynamically interesting but compositionally normal. Where does 3i Atlas fit? The nucleus size estimates range from 0.44 to 5.6 kilometers, quite uncertain but consistent with a small cometary nucleus. The composition, carbon dioxide rich with dust and traces of water and carbon monoxide, doesn't match typical solar system comets, which are water-dominated. The spectral reddening, slight excess reflection at longer wavelengths, could indicate organic compounds or specific mineral content. The polarization, that unprecedented deep negative branch, suggests scattering properties we've never seen. None of the established categories accommodate this combination. It's too active to be a dormant asteroid. It's too compositionally strange to be a normal comet. It's too symmetrical and structured in appearance to match typical active bodies. The smoothness paradox captures this perfectly. For a small rotating body ejecting gas and dust asymmetrically, you expect irregular shapes, brightness variations with rotation period, asymmetrical coma morphology, jet structures, time-variable features. Instead, observers claim near-symmetric halo, stable appearance, clean separation between core and envelope. That's not what small natural bodies do. Recent studies argue that 3i Atlas shows evidence of extensive galactic cosmic ray processing. This is a natural mechanism with radical consequences. Picture an object, any object, travelling through interstellar space for millions or billions of years. It's bathed continuously in high-energy particles, cosmic rays, protons and heavy nuclei accelerated by supernovae and other violent events. These particles penetrate surfaces, break chemical bonds, create new compounds, alter compositions. Carbon monoxide can be converted to carbon dioxide. Water ice can be broken down and reformed. Organic molecules can be synthesized from simpler components, building complex carbon chains and polymers. Over geological timescales, this cosmic ray processing builds up a crust, a rind of irradiated material that's chemically different from the interior. The surface becomes enriched in carbon dioxide and organics, depleted in water ice which gets converted or lost. The result is an object whose surface composition doesn't reflect its bulk composition, creating exactly the carbon dioxide-rich spectrum 3i Atlas shows. The crust could be darker and less reflective than fresh ice, or it could have unusual optical properties from the organic compounds. It might sublime differently than normal cometary ices, potentially explaining gentler outgassing or unusual dust behavior. This hypothesis is natural, requires no exotic physics or artificial intervention, and explains several of 3i Atlas's anomalies. The composition makes sense as a product of eons of radiation exposure. The polarization might reflect fine-grained organics or complex ice structures created by irradiation. The smooth appearance could come from a uniform processed crust that sublimates differently than rough unprocessed ice. It's a genuinely compelling explanation that places 3I Atlas in a new category: ancient interstellar wanderers, sculpted by radiation into something fundamentally different from anything that spent its life in our solar system. But cosmic ray processing doesn't explain everything. It doesn't obviously explain the missing tail, though maybe processed dust behaves differently. It doesn't explain the rigid core appearance or the sharp boundary of the halo. It doesn't address potential trajectory anomalies or rotational stability, if those prove real. It's a strong hypothesis for composition and surface properties, but leaves behavioral puzzles unresolved. Could 3I Atlas represent a completely new class of object? Not comet, not asteroid, not centaur or trans-Neptunian body, but interstellar relic, cosmic ray-aged, shaped by billions of years in the void between stars? If so, our taxonomy needs expansion. Our understanding of what kinds of small bodies exist in the galaxy needs revision. And the implications ripple outward, because if one interstellar relic shows these properties, others probably do too. Oumuamua might have been another one, explaining its weirdness through processing rather than artificial origin. Future interstellar visitors might show similar patterns. This forces a conceptual shift. We've been studying solar system small bodies and assuming they represent universal templates. Maybe they don't. Maybe objects that form around different stars, in disks with different compositions, then spend eons between stars getting irradiated and modified, end up looking nothing like what we're used to. Maybe 3I Atlas is our first clean look at that population, and our confusion reflects the limitation of our experience rather than the impossibility of the object. 3I Atlas might occupy a brand new category, bridging Comet and something else, natural and exotic, familiar and alien all at once. It forces us to expand our taxonomy of small bodies and acknowledge that the galaxy contains diversity we haven't sampled. If this interpretation holds, then every subsequent interstellar visitor will teach us something new, filling in a picture of galactic small body populations that we've barely begun to sketch. And the excitement isn't just about one strange object, it's about realizing that the universe is far more varied and interesting than our limited local sample suggested. 3I Atlas isn't just an oddball, it's a messenger showing us what's out there waiting to be discovered. Part 9. The Shadow Conversations in Agencies and Academia. Science is supposed to be transparent. Data gets collected, analysed, peer-reviewed, published, discussed openly. Theories get proposed, tested against observations, refined or discarded based on evidence. The process is messy but ultimately self-correcting because everything is visible and anyone can check the work. That's the ideal. The reality, especially when dealing with something as unprecedented and potentially controversial as 3I Atlas, is more complicated. Decisions get made behind closed doors about what to emphasize, what to downplay, what to investigate further before going public. Careers and institutional reputations rest on not being embarrassingly wrong, which creates pressure to be conservative, to wait for consensus, to avoid sticking your neck out on something that might turn out to be a processing artifact or observer error. Major institutions have invested substantial resources in studying 3I Atlas. NASA directed the James Webb Space Telescope, arguably the most powerful astronomical instrument ever built, to observe it. Heliophysics missions like STEREO and SOHO captured it in their wide-field images. The European Space Agency coordinated ground-based telescope time. Universities around the world tracked it, obtained spectra, measured positions, published papers. This represents millions of dollars in telescope time and person-hours of effort. That investment buys high-quality data, but also creates institutional momentum toward particular interpretations. The public messaging from these organizations has been remarkably consistent and remarkably bland. 3I Atlas is an interstellar comet. It has a coma of gas and dust. The nucleus is estimated to be a few kilometers across. The orbit is hyperbolic, confirming interstellar origin. The composition includes carbon dioxide, carbon monoxide, water, dust. No threat to Earth. Everything fits the comet model. Move along, nothing to see here beyond the inherent coolness of detecting another interstellar visitor. But contrast that official messaging with the analyses and discussions happening in less formal channels. Conference presentations where researchers show preliminary data with caveats and question marks. email exchanges between collaborators trying to make sense of anomalous results, forum discussions where amateur analysts share processing techniques and debate what they're seeing. These conversations reveal far more uncertainty, far more puzzlement, far more willingness to entertain unusual interpretations than the official press releases suggest. The critiques focus on exactly the features we've been exploring. Why is the polarization so extreme? Why does the composition differ so dramatically from solar system comets? Why aren't we seeing a proper dust tail given the confirmed outgassing? Why do some images show this rigid structure that doesn't match any comet we've studied? Why do all the unusual features coincide in one object rather than being scattered across many? Each question individually might have a natural answer, but collectively they create a pattern that's hard to dismiss. Institutional hesitation to explore these questions openly stems from legitimate concerns. Publish results suggesting something genuinely anomalous, and you invite intense scrutiny. If you're wrong, if it turns out to be instrumental error or processing artifacts or misinterpretation, your credibility suffers. Funding agencies might question your judgment. Peer reviewers might reject future papers more harshly. The media might sensationalize your claims, creating public misunderstanding that reflects poorly on you and your institution. The incentives push strongly toward caution, toward waiting until you're absolutely certain before making bold statements. This creates a dynamic where anomalies get investigated privately, discussed quietly, but not brought into the open until someone feels confident enough to stake their reputation on a claim. The problem is that building confidence requires data, and getting data requires telescope time, and getting telescope time requires convincing committees that your target is worth observing, and convincing committees is easier if you can point to published results suggesting something interesting. It's a chicken and egg problem that can trap genuinely anomalous objects in a kind of investigative limbo. Allegations circulate in fringe communities that certain data are being withheld. Early inbound images showing more structure than officially acknowledged. Full polarization maps across multiple wavelengths. Complete spectral coverage revealing composition details not yet published. Trajectory analyses including non-gravitational terms that don't match standard outgassing models. These allegations are unverified and possibly unfounded, but they gain traction because the disconnect between official blandness and observed strangeness feels too large to be accidental. There are legitimate reasons to withhold data temporarily. Instruments need calibration and characterization before data gets released. Proprietary observing time gives investigators first crack at publication to reward the effort of writing proposals and designing observations. Complicated analyses take time to complete properly. Peer review can take months or years. None of this is sinister. It's just how science operates when resources are limited and competition is intense. But the consequence of that secrecy, even legitimate scientifically motivated secrecy, is mistrust. When the public sees dramatic amateur images suggesting something extraordinary, while official channels show boring conventional comet behavior, conspiracy theories flourish. People assume cover-ups and suppression when the reality might just be methodological conservatism and different processing choices. The mistrust feeds back into fringe narratives, making it harder for institutions to communicate credibly even when they're being honest. A more transparent approach might serve everyone better. Publish raw data promptly even if analysis isn't complete. Acknowledge anomalies openly even if you don't have explanations yet. Admit uncertainty rather than projecting false confidence. Engage with amateur analysts respectfully rather than dismissing them categorically. These changes would build trust and might actually accelerate scientific progress by crowdsourcing analysis and enabling independent verification. The consequences of hesitation extend beyond 3i Atlas. If this object represents a genuinely new category of interstellar visitor or exhibits physics we don't understand, delay in recognition delays follow-up observations and delays theoretical development. Opportunities to observe it under specific conditions might be missed because telescope proposals weren't submitted in time. Other researchers might not realize its significance and ignore it in favor of more conventional targets. The scientific community might collectively fail to recognize something important because the institutional structure makes bold claims too risky. What if we're watching the birth of a new paradigm but won't realize it until years later, when dust settles and consensus emerges? Paradigm shifts in science don't happen smoothly. Thomas Kuhn taught us that anomalies accumulate. Old theories get stretched to accommodate them, and eventually someone proposes a new framework that fits the data better. 3i Atlas might be one of those accumulating anomalies, a data point that doesn't fit comfortably into existing categories and forces us to rethink our assumptions. But recognition might lag observation by years or decades, especially if the institutional machinery isn't set up to handle truly anomalous objects efficiently. Behind the polite certainty of official statements, there might be vigorous debate, genuine confusion, and competing interpretations. Some researchers probably think 3i Atlas is a perfectly normal, if compositionally unusual comet that just looks weird because of processing artifacts. Others might privately suspect it's something genuinely novel, but lack the data or confidence to say so publicly. A few might be entertaining exotic possibilities, while knowing that vocalizing them would damage their careers. All of this happens in shadow conversations, hallway discussions, email chains marked "Do Not Forward," Slack channels with carefully curated membership. That's where science actually happens, in the messy, uncertain space before consensus crystallizes. The public gets the sanitized version, the press release, the confident summary. But the reality is far more interesting, far more uncertain, and far more human than the official narrative suggests. Understanding 3i Atlas might require not just better data but a willingness to have those shadow conversations in daylight, where scrutiny and collaboration can accelerate understanding rather than fear of embarrassment slowing everything down. Part 10. The broader cosmic puzzle. Step back for a moment and look at the scoreboard. 3 confirmed interstellar objects in 8 years. 1i/Oumuamua in 2017, weird and elongated with unexplained acceleration and no coma. 2i/Borisov in 2019, perfectly normal comet behaving exactly as predicted. 3i Atlas in 2025, hybrid monster with comet-like composition and bizarre appearance and missing tail and unprecedented polarization. 3 data points, 3 completely different profiles. Either we've been spectacularly unlucky in our sampling, catching only the weirdest members of a mostly normal population, or interstellar space is filled with diversity that makes our solar system look boring and homogeneous by comparison. Statistics suggest we're only seeing a tiny fraction of what's out there. Detection requires objects to pass close enough to Earth, bright enough to spot, at a time when someone's looking in the right direction. The vast majority of interstellar visitors probably cruise through undetected, too faint or too far away, or moving through parts of the solar system we don't monitor continuously. So these 3 objects represent the tip of an enormous iceberg, samples drawn from a galactic population we've barely begun to characterize. Oumuamua taught us that not all interstellar objects are comets. Its lack of coma, unusual shape and trajectory anomalies defied easy categorization. Proposals ranged from solid rock tumbling through space to hydrogen iceberg to nitrogen, ice fragment to fragment of a shattered planet to artificial probe powered by solar radiation. None of the natural explanations fit perfectly. The artificial hypothesis, while extraordinary, at least explained the observations without requiring implausible coincidences. 8 years later, we still don't know what Oumuamua was, and it's long gone, unreachable, forever ambiguous. Borisov reassured us that conventional interstellar comets exist. It looked like a comet, acted like a comet, had the composition and behavior matching comets formed in planetary systems like ours. That one data point suggested maybe the galaxy is full of familiar objects, and Oumuamua was just an outlier. Except now we have 3i Atlas demolishing that comfortable assumption. Historical anomalies hint that strange inbound objects aren't new. Archival surveys from the 1990s and 2000s contain unexplained detections, objects with unusual brightening, odd polarization signatures, reflectance curves that don't match known categories. Most of these went unstudied because without confirming observations or follow-up data, they're just curiosities in databases. But looking back with fresh eyes, knowing that interstellar visitors exist and can be strange, some of those historical anomalies deserve re-examination. Were they misidentified asteroids? Were they interstellar objects that we fail to recognize? Were they something else entirely? Southern Hemisphere surveys, less systematically searched than northern ones, might hide more examples. Wide-field survey telescopes like Pan-STARRS and the upcoming Vera Rubin Observatory will catch far more interstellar visitors in coming years, building statistics that'll either confirm 3i Atlas as a rare oddity or reveal it as representative of a common class we didn't know existed. The Rubin Observatory alone is expected to detect several interstellar objects per year once fully operational, transforming this field from anecdote to statistical science. 3i Atlas might be a missing link, an object bridging Oumuamua-like bodies and classical comets. It has comet-like composition, outgassing, coma. But it also has weird structure, unusual appearance, behavioural anomalies that echo Oumuamua's strangeness. Maybe there's a continuum of interstellar objects ranging from pure rocky metallic bodies to hybrid processed comets to pristine icy comets, and we're seeing representatives scattered across that continuum. Understanding where 3i Atlas fits in that spectrum requires understanding what causes the differences. Cosmic ray processing is one mechanism. Objects spending eons in interstellar space get irradiated, surfaces altered, composition shifted. Depending on initial composition and exposure time, the result could be heavily processed crusts over pristine interiors, creating hybrid behaviour. Formation environment is another factor. Objects from low metallicity star systems might have different ice compositions. Objects from disrupted planetary systems might be fragments with unusual properties. Objects from failed planet formation might be pristine samples of protoplanetary disk material never incorporated into planets. Or maybe some fraction of interstellar objects aren't natural at all. Maybe technological civilizations build probes and send them between stars, and occasionally one passes through our neighbourhood. If even 0.01% of interstellar objects are artificial, and if interstellar visitors are as common as detection rates suggest, we should see artifacts on human civilization timescales. The challenge is recognizing them when we do. The implications of 3i Atlas being natural but exotic are profound for astrophysics. We'd learn that planet formation produces more diversity than we realized. We'd learn that interstellar processing creates new categories of objects with no solar system analogues. We'd learn that our theories, built on studying only our local cosmic backyard, need serious expansion. Polarization physics, comet activity models, dust dynamics, cosmic chemistry would all benefit from incorporating the lessons of an object that breaks our templates. If 3i Atlas turns out to be artificial, the implications are even larger. It would mean we're not alone, and that other technological species exist or existed in the galaxy. It would mean interstellar travel is achievable, and that probes can survive journeys between stars. It would raise immediate questions about who sent it, from where, when, and why, and it would utterly transform humanity's conception of its place in the universe overnight. But even if neither extreme holds, even if 3i Atlas is just a really weird natural object that we eventually explain with conventional physics, plus cosmic ray processing and unusual formation history, the lesson remains powerful. The galaxy is more diverse and surprising than we thought. Our sample of one solar system doesn't constrain the possibilities adequately. Interstellar space contains objects we haven't imagined, behaviours we haven't modelled, physics we're still learning. And 3i Atlas is showing us that every new visitor is an opportunity to expand our understanding, to challenge our assumptions, to ask better questions. The cosmic puzzle extends far beyond this one object. It's about building a galactic census of small bodies, understanding the distribution of compositions and structures and behaviours across different stellar environments and evolutionary histories. It's about preparing for future detections by developing better instruments, faster response protocols, more sophisticated analysis techniques. It's about recognising that the universe is full of surprises and that sometimes the most important discoveries come from things that don't fit our expectations rather than things that confirm them. 3i Atlas might not just be an oddball, it might be our first glimpse of a whole new class of interstellar wanderers, a population we've been blind to because we didn't know to look. And if that's true, the question isn't just what is this one object, but what else is out there waiting to confound us. Part 11, November 2025. The Sun emits a structured CME. The Sun is not a static light bulb, it's a roiling ball of plasma, magnetic fields tangling and snapping and reconnecting in violent events that hurl matter into space. Coronal mass ejections, CMEs, are among the most dramatic of these events. Billions of tons of magnetized plasma launched at speeds reaching thousands of kilometers per second, expanding as they propagate through the solar system, sometimes engulfing planets, disrupting satellites, creating auroras. We've watched thousands of CMEs over decades of solar observation. Most follow predictable patterns, blob-like structures with embedded magnetic fields, messy and turbulent but broadly understood. November 2025 brought something different. Heliophysics spacecraft monitoring the Sun detected a CME with unusual internal structure, a helical substructure that repeated at regular intervals across the ejected plasma cloud. Instead of the chaotic tangle typical of CMEs, this one showed organization, patterns that looked almost regular, almost designed. Magnetic field measurements revealed twisted field lines wrapped around each other like braided rope. Plasma density showed oscillations that corresponded to the magnetic structure. It was beautiful, striking, and scientifically puzzling because while helical structures do appear in solar phenomena, they're usually localized and short-lived, not maintained across an entire massive ejection. Why does this matter for 3I Atlas? Because that structured CME was launched roughly along the ecliptic plane, the same general region of space where 3I Atlas was traveling. Solar wind doesn't propagate uniformly. It carries structures, density variations, magnetic field configurations. A CME hitting a comet can dramatically alter its appearance and behavior. The dense plasma compresses the coma, pushes it back, disrupts tail formation. Strong magnetic fields can confine ionized gas, prevent normal expansion, create boundaries where none would otherwise exist. Turbulence can mix coma material, blur structure, or paradoxically create sharp transitions if conditions are right. If 3I Atlas was caught in the structured CME or in the disturbed solar wind following it, the effects could explain some of the visual anomalies. The smooth halo might be a magnetoplasma boundary, formed where solar wind pressure balanced outward coma expansion. The blue color could be ionized gas fluorescing, more strongly than normal due to enhanced UV flux during the CME. The missing tail might be suppressed because plasma pressure pushed everything back toward the nucleus, instead of allowing normal tail development. The rigid appearance of the core could be contrast effect, where the compressed bright coma makes the nucleus look sharper by comparison. This environmental explanation is attractive because it doesn't require 3I Atlas itself to be unusual. Any comet experiencing similar solar wind conditions might exhibit similar appearance. The strangeness would be circumstantial, a matter of being in the wrong place at the wrong time when the Sun was doing something interesting. Testing this hypothesis requires checking whether other objects in similar regions showed similar effects, or whether observations of 3I Atlas before and after the CME impact showed appearance changes. But there's a complication. If solar environment fully explains the appearance, we'd expect rapid variability. CME effects last hours to days as the structure passes. The solar wind settles back to normal afterward. If 3I Atlas looked strange only during CME passage and normal before and after, that would strongly support environmental causes. But if it looked strange consistently across multiple observation epochs under varying solar conditions, environment alone can't explain it. The intrinsic properties of the object must contribute. The broader lesson is that interpreting observations of solar system objects requires accounting for dynamic environmental conditions. The Sun is not a constant background. It's an active, variable star that modulates the environment every object experiences. Radiation levels change with solar cycle. Solar wind pressure varies with activity. CMEs and solar flares create transient conditions that can dramatically affect comet behavior. Interstellar objects are particularly interesting because they haven't adapted to our Sun. They formed around different stars with different radiation spectra and different wind properties. When they encounter our solar environment, the interaction might produce outcomes we've never seen with solar system natives. This introduces ambiguity into every observation. Is a feature intrinsic to the object or imposed by environment? Is anomalous behavior reflecting unusual object properties or unusual solar conditions at that moment? Separating intrinsic from environmental requires multiple observations over time under varying conditions which we often don't have. 3I Atlas passed through quickly. Most observations clustered around perihelion when solar interaction was strongest. Disentangling cause and effect becomes genuinely difficult. The structured CME serves as a reminder of cosmic complexity. We can't treat objects as isolated specimens under laboratory conditions. They're embedded in dynamic environments that actively shape what we observe. Even if 3i Atlas is intrinsically exotic, an interstellar relic with processed crust and unusual composition, its appearance at any given moment results from the interaction between those intrinsic properties and the local solar environment. Understanding the object requires understanding the environment, and vice versa. This also means that some features we're attributing to 3i Atlas might not be reproducible. If we encountered another object identical in composition and structure, but under different solar conditions, it might look completely different. The missing tail, the smooth halo, the blue glow might all be contingent on specific environmental factors present during our observations. Future interstellar visitors might show totally different appearances even if they're similar objects, simply because solar activity differs. The November-structured CME blurs the line between object anomaly and observational anomaly in ways that demand humility. We can't claim certainty about intrinsic properties when environment is uncontrolled and variable. The most honest assessment acknowledges multiple contributing factors, intrinsic strangeness potentially amplified or modified by environmental dynamics. 3i Atlas might be weird, but the Sun might have made it look weirder than it really is. Or the Sun might have masked weirdness that would be more obvious under calmer conditions. Without controlled experiments, which are impossible for unique objects passing through once, we're left making probabilistic arguments based on incomplete data. The cosmos is not trying to make our job easy. The universe conspires, not maliciously but indifferently, to create observational challenges that prevent simple interpretations. The Sun, our own star, becomes part of the mystery rather than a neutral background. And that complexity is why studying 3i Atlas remains fascinating and frustrating in equal measure. Every answer generates new questions, and even when we think we understand something, solar activity reminds us that we might be observing a performance shaped as much by the stage and lighting as by the actor itself. Part 12. The breakthrough in neutrino directional imaging. Light has been our primary tool for exploring the universe since Galileo first pointed a telescope at the sky. Photons carry information across cosmic distances, encoding data about temperature, composition, motion, magnetic fields. We've gotten extraordinarily good at collecting and interpreting photons across the spectrum from radio to gamma rays. But light has limitations. It interacts with matter, getting absorbed or scattered by dust and gas. It can be distorted by lensing or mimicked by various emission mechanisms. And most critically, for questions like 3i Atlas, light only shows us surfaces and atmospheres. Interior structure, internal energy generation, processes happening beneath opaque layers remain hidden from electromagnetic observation. Neutrinos change that equation entirely. These nearly massless, almost non-interacting particles pass through matter like ghosts. Produced in nuclear reactions, particle collisions, radioactive decay, neutrinos escape from regions where light cannot. The Sun's core produces neutrinos that reach Earth 8 minutes later, having travelled straight through 600,000 kilometres of dense solar plasma without deviation. A supernova's collapse generates a neutrino burst that escapes hours before the light does because neutrinos don't interact with the collapsing star's envelope. For astronomy, neutrinos offer a window into hidden processes. The challenge has always been detection. Precisely because neutrinos barely interact with matter, catching them requires enormous detector volumes and long exposure times. Existing neutrino telescopes like IceCube buried in Antarctic ice or Super Kamiokande in Japanese mines can detect neutrinos from cosmic sources, but with very poor directional resolution. You know a neutrino arrived and roughly its energy, but pinpointing where it came from requires statistical analysis of many events. For a single object, like 3i Atlas, traditional neutrino astronomy is nearly useless. Enter 2025 with reports of breakthrough development in directional neutrino imaging. Experimental prototypes using novel detection techniques, potentially involving quantum sensors or exotic tracking geometries, claim ability to resolve neutrino sources with angular precision approaching degrees rather than tens of degrees. This is speculative, cutting-edge technology that hasn't been fully validated, but if it works, it transforms neutrino astronomy from statistical science to imaging science. You could point a neutrino telescope at a specific object and ask, is it emitting neutrinos? How many? What energies? What does that imply about internal processes? Why does this matter for objects like 3i Atlas? Because if the object is artificial, if it contains reactors or computers or propulsion systems, those technologies might generate neutrinos. Fusion reactors produce copious neutrinos from deuterium and tritium reactions. Fission reactors produce neutrinos from beta decay of fission products. Even exotic propulsion concepts like antimatter annihilation or black hole drives would generate characteristic neutrino signatures. Natural objects, by contrast, generate minimal neutrinos. Cometary ices and rocks don't have energy sources producing neutrino flux above cosmic background. Directional neutrino imaging could detect dark activity, processes invisible to electromagnetic telescopes. Imagine 3i Atlas, passing through the inner solar system, appearing visually ambiguous, spectroscopy showing coma but anomalous composition, polarimetry showing unprecedented scattering, trajectory showing possible unexplained acceleration. Now add neutrino telescope detection. Steady flux of MeV-range neutrinos from the object's direction, energy spectrum matching fusion reactions. That would be nearly definitive evidence of artificial power generation, far stronger than ambiguous optical signatures. Conversely, non-detection of neutrinos when you'd expect them if artificial systems were present provides powerful constraints. If 3i Atlas were a powered spacecraft using nuclear systems, failure to detect neutrinos would require either the systems are shut down, or they use technology that doesn't produce neutrino signatures, or our neutrino telescope isn't sensitive enough. Each scenario has different implications and probabilities. The technical challenges remain immense. Neutrino flux from any small object at astronomical unit distances would be incredibly faint. Cosmic neutrino background and solar neutrinos create noise that must be distinguished from target signal. Directional resolution, even with breakthrough techniques, needs validation and calibration. Exposure times might need to be impractically long, but the principle is sound. Neutrinos offer information orthogonal to electromagnetic observations, providing independent verification or falsification of hypotheses about object nature. This forward-looking technology also highlights how transient opportunities can be. 3i Atlas came and went. If directional neutrino telescopes had existed and been sensitive enough, we could have observed it. Now it's too far away, signal too weak, opportunity lost. Future interstellar visitors will benefit from technologies we're developing now. The lesson is that preparing for rare events requires maintaining diverse observational capabilities so that when something genuinely anomalous appears, we can study it with every tool available, rather than regretting what might have been detected if only we'd had the right instrument ready. Neutrino astronomy also represents a philosophical shift. For centuries, astronomy meant collecting light. Objects that didn't shine brightly were hard or impossible to study. Dark objects, cold objects, shrouded objects remained mysterious. Neutrinos democratize observation, making internal processes and hidden energy sources accessible. If 3i Atlas or similar objects operate using physics we don't fully understand, neutrino signatures might reveal that physics even when optical appearances remain ambiguous. The speculative but grounded possibility of neutrino imaging reframes the entire mystery. What seems invisible today might be detectable tomorrow. What looks like a comet in visible light might reveal internal structure through neutrinos. What appears passive might show activity in particles that ignore surfaces and shielding. Deciding what E3i Atlas is might require not just better optical telescopes or more sensitive spectrographs, but entirely new detection modalities that haven't been invented yet. Science advances by expanding the range of questions we can ask and phenomena we can measure. 3i Atlas, and the mysteries it embodies, drive that expansion by showing us the limits of current capabilities and motivating development of next-generation tools. And when those tools arrive, objects that seemed inexplicable today might yield their secrets readily, or they might reveal even deeper mysteries that require yet another generation of innovation to unravel. Part 13. AI models predicting stellar instabilities. Months in advance. The universe is not just strange, it's also more predictable than we often realize if you have the right models. Stars undergo instabilities, magnetic reconnection events, oscillation modes that lead to flares and mass ejections on timescales ranging from minutes to years. Traditionally, predicting these events required solving complex magneto-hydrodynamic equations, simulating plasma behavior under extreme conditions, computing how magnetic fields evolve and interact. The calculations are computationally intensive and often inaccurate because small uncertainties in initial conditions amplify over time. We could model stellar behavior in general, but struggled to predict specific events for specific stars at specific times. 2025 has seen remarkable progress in applying machine learning to astrophysics. Physics-informed neural networks, AI systems trained not just on data, but also on fundamental physical laws, have achieved breakthroughs in predicting solar flares and stellar microbursts. By ingesting decades of solar observation data, learning the patterns that precede eruptions, and incorporating physics constraints like magnetic flux conservation and energy balance, these models can now forecast solar activity days to weeks in advance with surprising accuracy. Some experimental systems claim even longer prediction horizons, months ahead, for specific types of stellar instabilities. If a star shows patterns in its magnetic field evolution or oscillation modes that historically preceded eruptions, AI can recognize those patterns early and issue forecasts. This isn't magic, it's pattern recognition operating on vastly more data with more sophisticated feature extraction than human observers can manage manually. But the practical impact is transformative. Why does this matter for 3i Atlas? Because the object's environment, the radiation and particle flux it experiences, varies dramatically with solar activity. Solar flares increase UV flux, ionizing more coma material, potentially enhancing fluorescence or creating plasma effects. Coronal mass ejections compress comas, disrupt tails, modify the boundaries of interaction regions. If we could predict when solar activity would affect 3i Atlas, we could plan observations to catch the object under specific conditions. Imagine AI forecasting a major CME launch along the ecliptic 3 weeks in advance. Observers could prepare, securing telescope time, tuning instruments, coordinating multi-wavelength campaigns to capture 3i Atlas before, during, and after CME impact. That would provide the time-resolved data needed to separate intrinsic from environmental effects, answering questions about whether strange appearance is persistent or transient, object-caused, or environment-caused. This also opens possibilities for long-term monitoring of interstellar visitors. Objects like 3i Atlas won't return. They pass through once and leave forever. But as they travel outward, crossing different heliocentric distances, they experience changing solar wind conditions, radiation levels, particle densities. AI-enhanced forecasting of those conditions allows observers to predict when interesting interactions might occur, targeting observations efficiently rather than hoping to catch something by luck. There's a deeper implication too. If solar environment significantly affects object appearance, and if we can forecast that environment, then observations made during forecasted quiet periods should reveal intrinsic properties more clearly. Wait for solar minimum, target the object when solar wind is calm, UV flux is low, CMEs are rare. Under those controlled-ish conditions, what you see is more likely to reflect the object itself rather than environmental modulation. AI becomes a tool for creating observational windows where natural variability is minimized. But this cuts both ways. If 3i Atlas suddenly reactivates years from now when it's far from the Sun, what could cause that? Natural mechanisms struggle to explain activity at large heliocentric distances where solar heating is negligible. But if the object encounters a region of enhanced cosmic ray flux, or passes through a density filament in interstellar space, or experiences interaction with the heliopause, those events might trigger observable changes. AI models tracking not just solar but interstellar conditions could alert us to such possibilities, enabling observations that would otherwise miss transient phenomena. Imagine monitoring 3i Atlas for years as it exits the solar system. Most of the time it's inactive, cold, boring, but AI predicts it'll pass through a region of enhanced galactic cosmic ray flux in 6 months. Observers mobilize, pointing sensitive instruments, watching for changes, and indeed, radiation triggers sublimation of buried ices or fluorescence of surface organics, creating a brief reactivation event that reveals composition and behavior impossible to study during perihelion when solar effects dominated. That single forecasted observation might answer more questions than months of random monitoring. This represents a shift from reactive to proactive astronomy. Historically, we've responded to events after they happen. Supernova explodes, we observe it. Comet brightens, we study it. Object transits, we catch it if we're lucky. AI-enhanced forecasting flips the script, enabling preparation and coordination that maximizes science return from rare or transient phenomena. For interstellar objects, which appear unpredictably and leave permanently, this capability could be transformative. The challenge is validation. AI models are only as good as their training data and underlying physics assumptions. Predictions require testing against reality, building confidence through verified forecasts before trusting high-stakes decisions to AI recommendations. False positives waste resources. False negatives mean missed opportunities. But over time, as models improve and validation accumulates, the balance shifts toward trust. There's also philosophical significance. Predicting cosmic events implies understanding their causes, or at least recognizing patterns that correlate with causes. When AI successfully forecasts stellar instabilities, it's revealing hidden structure in complex systems, making the universe more comprehensible and less arbitrary. That understanding feeds back into theory, suggesting mechanisms and interactions that human theorists might then formalize. AI becomes partner in scientific discovery, not just tool but collaborator that sees patterns humans miss. For 3i Atlas, the immediate value lies in optimizing limited observational resources. Telescope time is precious. Instruments can't stare at one object forever. AI forecasting enables strategic allocation, observing when conditions are likely to be scientifically interesting, standing down when nothing new is expected. Over time, this approach will accumulate far more useful data per unit investment than random monitoring, accelerating understanding of transient and variable phenomena. And if the universe continues surprising us with objects like 3i Atlas that defy simple categorization, AI-enhanced real-time monitoring will become essential. Human attention is finite. Automated systems can watch continuously, flagging anomalies for human follow-up. Combined with predictive models, this creates a responsive observational network that adapts to changing conditions and emerging mysteries. We're entering an era where AI augments human curiosity, enabling investigations at scales and speeds previously impossible. 3i Atlas might be the kind of object where that augmentation makes the difference between solving the mystery and watching it slip away unsolved into interstellar darkness. Part 14. The strange gamma flash over the Arctic. Sometimes the universe just throws you a curveball. November 2025. High-altitude balloon detectors over the Arctic, part of a long-running atmospheric science campaign, registered something that made researchers check their instruments and each other's data to confirm they weren't seeing things. An ultra-short gamma-ray flash, milliseconds in duration, energies in the low MeV range, too weak to be a classical gamma-ray burst from a distant galaxy, too structured and brief for atmospheric lightning, too sharp and localized for known cosmic ray air showers. It didn't match any template. The data came from multiple synchronized stations, eliminating single detector malfunction as explanation. The energy spectrum had features, peaks and valleys suggesting source physics rather than random noise. Directionality pointed roughly toward a region of sky rather than being uniform background. But there was no accompanying signature of charged particle showers, no secondary detection by ground arrays, no optical or radio counterpart. Just this brief, intense gamma-ray pulse that appeared and vanished like it was never there. Explanation struggled. Terrestrial gamma-ray flashes, TGFs, associated with thunderstorms can produce gamma rays through runaway electron acceleration in electric fields, but this event happened in clear weather, no storms within hundreds of kilometers. The energy spectrum didn't match TGF profiles. Solar flares emit gamma rays, but the sun was quiet that day, and the directionality was wrong anyway. Gamma-ray bursts from cosmic sources are immensely energetic but also immensely distant, producing characteristic long duration or double-peaked profiles that this event lacked. Exotic astrophysics offers possibilities, maybe a small magnetoflare, magnetic field reconnection on a neutron star releasing gamma rays. But magnetoflares are usually detected across electromagnetic spectrum, not just gamma rays. Maybe primordial black hole evaporation, though those are purely theoretical and expected to be even rarer than detection rates allow. Maybe dark matter interaction, particles annihilating or decaying in Earth's atmosphere. but dark matter signals should be steady or slowly varying, not millisecond flashes. Or maybe something artificial. Propulsion systems using antimatter or high-energy plasma might produce gamma-ray signatures. Energy releases from spacecraft systems, accidental or deliberate, could create brief, intense flashes. But this requires assuming technological sources operating in Earth's vicinity, which has exactly zero confirmed precedent, and requires extraordinary justification. What connects this to 3i Atlas? Speculatively, thematically, the connection is about recognizing that cosmic phenomena don't always announce themselves clearly. High-energy transients, whether gamma-ray flashes or weird cometary appearances, challenge our categories and demand open-minded investigation. If interstellar space contains objects or processes we don't understand, we should expect occasional detections that don't fit templates, that leave us scratching heads, that resolve only with time and better data. The gamma flash reminds us that the solar system neighborhood, even near-Earth space, might host energetic phenomena we haven't catalogued. Interstellar objects passing through could potentially trigger or emit high-energy radiation under specific conditions. Cosmic ray interactions with coma material, magnetic reconnection in plasma sheaths, radiation from internal processes if the object is artificial, all could produce transient gamma-ray emissions detectable by sensitive instruments. Connecting specific events is speculative without direct evidence. The Arctic Flash and 3i Atlas weren't coincident in time or direction. But the broader point stands: the universe is reactive, alive with transient events, many of which we catch only by accident or miss entirely. If 3i Atlas emitted gamma-ray flashes during its passage, and no detector happened to be looking at the right time, we'd never know. Conversely, if we detected gamma rays from its direction and attributed them to unrelated background, we'd miss crucial evidence about its nature. This suggests need for all-sky, all-time, multi-messenger monitoring. Not just optical telescopes tracking specific targets, but networks of detectors sensitive to various phenomena, continuously recording, using AI to flag anomalies for human attention. Only with comprehensive coverage can we catch coincident or correlated events that reveal connections between seemingly unrelated phenomena. The gamma flash also serves philosophical function, reminding us that absence of explanation doesn't mean absence of significance. Science progresses by accumulating anomalies, puzzling over them, eventually connecting dots into patterns that reveal new physics or new types of objects. One unexplained flash is curiosity. Multiple flashes with similar properties become pattern. Pattern plus theory becomes discovery. But we only get there by taking anomalies seriously rather than dismissing them as noise. For 3i Atlas, the lesson is to keep open mind about what kinds of signatures might be associated with it. Visible light and infrared show one face. Spectroscopy shows another. Polarimetry adds a third dimension. Neutrinos, if we could detect them, would add a fourth. Gamma rays, whether from the object itself or from interactions it triggers, represent yet another channel. Each channel carries information, and only by combining them do we build complete picture. The Arctic Flash may have nothing to do with 3i Atlas. It might be unrelated atmospheric phenomenon, instrumental artifact, misidentified mundane event. But the coincidence of timing, November 2025 when 3i Atlas was dominating astronomical discussion, the strangeness of both events, the lack of easy explanations for either, creates at minimum a narrative resonance. We're living through a period where cosmic mysteries are accumulating faster than solutions. Either we're experiencing statistical clustering of rare events, or we're witnessing connected phenomena that we don't yet have framework to understand. The universe occasionally bursts with strange signals, and perhaps objects, like 3i Atlas, are part of a broader network of high-energy events and exotic physics that we're only beginning to detect. Whether connection is real or imagined, the exercise of considering possibilities, looking for correlations, thinking creatively about data moves science forward. Anomalies don't always resolve neatly. Sometimes they linger for decades, but they're the seeds of paradigm shifts, the hints that our current understanding is incomplete. 3i Atlas and the Arctic Gamma Flash may both be symptoms of that incompleteness, breadcrumbs leading toward discoveries we can't yet imagine. And that possibility, however uncertain, is what keeps researchers looking up, monitoring, analysing, wondering what the next surprise will be, and whether this time we'll be ready to understand it. Part 15. The new quantum vacuum propulsion test. Let's end with a glimpse of future possibilities, because understanding 3i Atlas might ultimately require understanding technology we haven't invented yet. 2025 has seen experimental labs testing concepts that sound like science fiction, but rest on genuine physics, however speculative. Quantum vacuum propulsion, the idea of extracting thrust from vacuum energy fluctuations without expelling propellant, has moved from purely theoretical speculation to laboratory experimentation. The results are preliminary, contested, tiny, but tantalizing. The theoretical foundation involves quantum mechanics prediction that vacuum isn't empty. Even in the absence of matter and radiation, quantum fields fluctuate, creating and annihilating virtual particle pairs. These fluctuations produce measurable effects like the Casimir force, where parallel conducting plates attract due to imbalance in vacuum fluctuations between and outside the plates. If you could manipulate vacuum fluctuations asymmetrically, you might extract net momentum, creating thrust without ejecting mass. Several experimental groups claim to have measured small forces in devices designed to exploit this principle. Thrust levels are measured in micronewtons at best, barely above noise, but proponents argue the principle is demonstrated even if practical applications remain distant. Skeptics counter that systematic errors, thermal effects, electromagnetic interference could explain the results without invoking exotic physics. The debate continues, as it should, with replication attempts and more rigorous controls. If quantum vacuum propulsion or something like it proves real and scalable, the implications for interstellar travel are revolutionary. Conventional rocketry requires carrying propellant, which mass constrains missions. Chemical rockets can't reach high speeds without enormous fuel mass. Nuclear propulsion helps, but still requires reaction mass. Light sails require intense lasers or close stellar passes. But propellantless systems, if they work, eliminate the tyranny of the rocket equation. You could accelerate continuously without fuel limits, reaching relativistic speeds given enough time and power. Now imagine encountering an interstellar probe using technology like this. It wouldn't have visible exhaust plumes, no glowing ion drive, no trail of ejected mass, just the object, moving under power but leaving no obvious signature of propulsion. From distance, you'd see something accelerating or maintaining trajectory against perturbations, but can't identify the mechanism. That's exactly the profile some observers claim for 3i Atlas: possible trajectory control, stable rotation, no obvious propellant expenditure, composition that doesn't scream artificial but doesn't entirely rule it out. The smooth halo could be plasma or electromagnetic shielding rather than dust hail. The blue glow could be ionization from high-voltage systems, or interaction with vacuum drive fields. The lack of tail could be because there is no exhaust, no ejected material, just field effects that don't produce visible signatures. The rigid core could be actual structural integrity, a manufactured object maintaining shape under acceleration, rather than loose rubble held together by weak gravity. But let's be clear about limitations. Quantum vacuum propulsion remains highly speculative, experimental, and controversial. No consensus exists that it works. Even if it does, scaling to spacecraft-sized systems faces enormous engineering challenges. Power requirements might be prohibitive, efficiency might be too low, side effects might make it impractical, and most critically for 3i Atlas, we have exactly zero evidence connecting it to any such technology. This is speculation layered on speculation, hypothetical technology applied to ambiguous observations. The value lies not in claiming. 3i Atlas uses vacuum drives, but in recognizing that our technological imagination constrains what we consider possible. When we picture interstellar probes, we default to familiar concepts: rockets, lasers, solar sails. But alien civilizations, if they exist, might have developed propulsion systems we haven't imagined or physics we don't understand. Encountering their technology would be confusing precisely because it doesn't match our templates. This also works in reverse. As human technology advances, we develop capabilities that might someday replicate what we observe in cosmic oddities. If vacuum drives or similar exotic propulsion become real, humanity will eventually launch interstellar probes that look and behave like what we're puzzling over with 3i Atlas. Future archaeologists studying the historical record might note that we encountered strange objects in the 2020s and simultaneously developed technologies that could explain them, and wonder whether the encountering and developing were connected, whether seeing stirred imagination or imagination prepared us to recognize what we were seeing. Whether 3i Atlas is natural or artificial, Comet or craft, the fact that we're now seriously testing propulsion concepts that could power interstellar travel tells us something profound. The gap between what we observe in the cosmos and what we can technologically achieve is narrowing. Science fiction becomes science fact on timescales measured in decades. Technologies that seemed impossible when our grandparents were born are mundane now, and technologies we test in labs today might enable interstellar exploration within our grandchildren's lifetimes. 3i Atlas might be a natural object shaped by billions of years of cosmic ray processing into something we've never seen before. It might be an artifact from another civilization, a probe sent eons ago on a one-way journey through the galaxy. Or it might be something in between, natural but so exotic that it challenges our categories and forces us to expand our understanding of what's possible. Regardless of which proves true, the mystery drives us forward, motivating better instruments, more sophisticated theories, more open-minded inquiry into the nature of reality. What if human curiosity catches up to the mysteries of the cosmos just as they catch up to us? What if the strange objects we're detecting now, the anomalies we're struggling to explain, are heralds of an era where humanity joins the community of spacefaring civilizations, where our probes begin appearing in other systems' skies, where the distinction between observer and observed blurs? 3i Atlas, whatever it is, reminds us that the universe is larger and stranger than our theories encompass. It challenges us to look harder, think deeper, imagine more boldly. And whether we solve its mystery tomorrow or centuries from now, the journey of trying, the process of questioning everything we thought we knew, is itself the discovery. Because in the end, science isn't about having all the answers. It's about having the courage to keep asking questions even when the answers might change everything we believe about our place in the vast, mysterious, endlessly surprising cosmos we call home.